Now, do you remember this legendary number of 300,000 kilometers per second? That's the speed of light. Well, we're often taught that this is the ultimate limit of the universe, as if some galactic police officer has put up a no passing sign in space. Many still believe this is just a technical barrier, that if we had enough energy, enough power, one day we'd overcome it. But I'm here to reveal a truth. This perspective is fundamentally completely wrong. In fact, calling it the speed of light is probably one of the biggest marketing blunders physics has ever made. Light isn't special here. It's just a messenger that obeys the rules, not the one who makes them. So what is this number, really? It's not merely a speed, but a fundamental conversion factor. It's the geometric structure of reality, the speed of causality, and also the speed of the very present moment we're living in. Just imagine, if you could exceed this limit, you wouldn't just be moving faster. You'd break the entire operating logic of the universe. You'd witness events happening before their causes, perhaps even killing your grandfather before you were born. At that point, the universe would no longer be the coherent story we know, but would turn into an inexplicable mess. In the next few minutes, we'll dissect this reality together, piece by piece, to uncover its profound mysteries. We'll explore how a seemingly simple observation of Jupiter's moons shattered the notion of absolute time. And here's an even bigger surprise. Right now, you are moving at the speed of light, but not in the way you think. To truly understand light, we first need to grasp the nature of motion. And to decipher motion, we cannot help but mention a great figure who connected all the pieces of the universe together. Yes, that's Isaac Newton. Before his time, humanity's worldview was clearly divided into two parts. On one side was Earth, where all heavy objects fell and eventually stopped. And on the other side was the sky, the realm of perfect, eternal, celestial bodies, which orbited forever without ever falling. But Newton had a stroke of genius, a question that changed everything. What if they were all one? Look at our moon. It seems to float peacefully in the sky, doesn't it? But the astonishing truth is that it's in perpetual free fall. This is quite a difficult concept to grasp. Now, how can an object fall forever without ever hitting the ground? To visualize this, imagine you're standing on top of a giant mountain. You throw a stone, it flies a few meters, and then quickly falls to the ground. You throw it harder, and the stone will fly further. But no matter what, gravity will still pull it back to the ground. Now imagine you have the arm of a giant. You throw the stone with such force, so fast, that while gravity is still pulling it down, the curvature of the Earth has already slipped beneath it. The stone is still falling towards Earth, but the Earth is continuously curving away underneath. What's the result? The stone just skips off the ground. It keeps sliding forever without ever touching down. That's an orbit. A continuous fall, but one that never successfully reaches its target. Newton performed a revolutionary calculation that completely changed the history of science. He knew that our moon was 60 times further away from Earth. With a brilliant hypothesis, he proposed that gravity spreads through space and weakens with the square of the distance. This means that if you're 60 times further away, the gravitational force will be 3,600 times weaker, which is 60 squared. We know that on Earth, an object falls about 5 meters in 1 second. So Newton posed the crucial question. If gravity at the moon's position is 3,600 times weaker, how much would the moon fall relative to a straight line each second? He performed a simple calculation, 5 meters divided by 3,600, and the result was about 1.3 millimeters. Then he looked up at the night sky and carefully measured the moon's actual orbit. He precisely calculated how much the moon deviated from its straight path each second. And would you believe it? The results matched perfectly, exactly 1.3 millimeters. Did you know that for the first time in human history, a mathematical law discovered on Earth could be applied with astonishing accuracy to the entire vast universe? This changed everything. So what did Newton do? He unified the entire universe, asserting that gravity was an instantaneous, universal, and absolute force, governing everything from falling apples to planets. But was there an invisible flaw in Newton's perfect universe that he overlooked? For centuries, a belief was deeply ingrained in human minds. That light was instantaneous. Have you ever thought that when you flip a light switch, light instantly fills every corner? Our eyes have always told us that, haven't they? But then in 1676, a Danish astronomer named Ole Rømer discovered an anomaly, a puzzling discrepancy. What happened? He was diligently observing Io, one of Jupiter's moons. Io was like a perfect cosmic clock, orbiting Jupiter with beat-by-beat precision. You could perfectly set your clock by Io. Yet Rømer noticed something extremely strange, a phenomenon that couldn't be explained by conventional knowledge. What puzzled him? When Earth moved closer to Jupiter in its orbit, Io's clock seemed to run faster, with eclipses appearing earlier than expected. Conversely, when Earth moved farther from Jupiter, this clock seemed to slow down, sometimes by as much as 22 minutes. Why this astonishing discrepancy? Many contemporary astronomers believed this was merely a calculation error, or perhaps Io's orbit wasn't as regular as people thought. But Romer bravely rejected all those hypotheses. He asserted celestial mechanics were perfect. It was our perception of the universe that was flawed. So what did Romer see that others didn't? He realized that Io's image needed time to travel to our eyes. And when Earth was farther from Jupiter, light had to traverse a much greater distance. That 22-minute delay wasn't caused by the moon Io. Instead, it was the time light needed to travel through the vacuum of space. A groundbreaking discovery. This was truly a monumental discovery, wasn't it? It proved that light isn't instantaneous, but has a finite, measurable speed. So what does this mean for us? It means that when you gaze up at the vast universe, you're not seeing the present. Instead, you're looking directly into the past. The sun you see in the sky is actually 8 minutes old. And Jupiter, its image is already 40 minutes in the past. Even the distant stars we admire could be centuries old. We are trapped in a perceptual bubble where the present is always the past. The concept of a universal present that Newton once believed in had completely collapsed. Clearly, all information requires time to travel through the universe. And then in the 19th century, another genius emerged, James Clerk Maxwell. What did he do? He precisely calculated this speed of light. Using groundbreaking equations of electromagnetism, Maxwell found a specific number, a precise value for the speed of light. Are you curious what that number is? A constant. It sounds simple, but what exactly is this constant? Compared to what? That this is where what you consider common sense will begin to waver? Let's delve deeper into the heart of this paradox. You'll find your intuition will be completely challenged. In our familiar world, velocities always add up simply, right? This is the principle of Galilean relativity. Imagine you're on a train, speeding along at 100 km/h, and you throw a ball forward. If the ball travels at 20 km/h relative to you, then to someone standing on the platform, it will move at 120 km/h. 100 plus 20 equals 120. Perfectly logical, right? Our intuition tells us so. But what happens if we replace the ball with light? The train is still moving at 100 km/h. You shine a flashlight forward. The light emits at velocity c. So to the person on the platform, how fast will the light be moving? Your intuition would say it's the speed of the train plus the speed of light, right? But the universe unequivocally answers no, it's still just the speed of light. No matter how fast the train is moving, even if it's hurtling along at 99% the speed of light, the light emitted from that flashlight will still always travel at velocity c relative to you and also at velocity c relative to the observer on the platform. Mathematically, this is completely impossible unless some other factor has changed. If velocity is distance divided by time and the speed of light is constant, then distance and time must change. This is what Einstein realized, and it was truly groundbreaking. For the speed of light to remain constant for all observers, space and time must be warped. This means that if you move extremely fast, your time will pass slower than mine. The space around you will also contract. Your second suddenly becomes longer than my second, and your meter becomes shorter than my meter. Do you believe in the extraordinary? This isn't an illusion, but a real physical phenomenon. Let's explore muons, particles born high in the atmosphere, yet only existing for a few millionths of a second. With such a short lifespan, they shouldn't be able to reach the ground before decaying. Yet, strangely, we still find them here on Earth. What's the mystery behind this? The answer lies in their incredible speed, nearly the speed of light. And what does that mean? For these particles, time seems to slow down in an unbelievable way. It's precisely this time dilation that allows them to exist long enough to traverse the entire atmosphere. But did you know the speed of light isn't just an ordinary travel speed, it's an invariant constant of the universe. Imagine it as a central pivot around which everything else in reality, from time to space, must bend and adjust to fit. But why is that? What makes it so special? Why does the universe impose an absolute speed limit? And why is that number precisely 300,000 kilometers per second rather than some infinite speed? To truly grasp this mystery, we need to change our perspective. Let's no longer view space and time as two separate concepts. Try to imagine you're behind the wheel of a car. You're on a vast salt flat, and ironically, your car's cruise control is stuck. Yeah, that means you always have to move at maximum speed, let's say 100 kilometers per hour. If you decide to drive straight north, your entire will be dedicated to the north, with none for the east. But if you start to gradually turn east, your speed will be split, a portion for the north and a portion for the east. And if you turn completely east, then your entire 100-kilometre march will be dedicated to the east, with none left for the north. The important thing is that you cannot increase your total speed. You can only divide it between the two directions, north and east. Do you see the analogy? Our universe operates in exactly the same way, but the two directions here aren't north and east. They are space and time. According to the theory of relativity, every object in the universe, from you, me, Earth to a distant star, is moving through space-time at a constant velocity. And this absolute velocity is precisely the speed of light we've been talking about. We are all in constant motion. But look at yourself right now. You're sitting still, not moving through space at all, right? In that case, your entire speed is being directed towards time. You are traveling into the future at the maximum possible velocity, 1 second per second. But what happens if you start moving through space, for example, when you launch yourself on a rocket? Then you are forced to change your velocity vector, and to do that you have to borrow some speed from time. Just like the car on the salt flat, that borrowed speed will be dedicated to moving through space. What does this mean? The faster you move through space, the less speed you have left to advance through the flow of time. And this is precisely why time slows down when we move at high velocities. So, if you reach the maximum limit in space, which is the speed of light, what happens then? At that point, you will have no speed left to dedicate to time. Amazingly, at the speed of light, time completely stops. For a photon, the concept of time simply doesn't exist. Consider this. The moment a photon is emitted from a distant star and the moment it hits your eye, that is the same moment. For light, the entire universe is instantaneous. There is no flow of time whatsoever. And this is why you, an entity made of matter, will never be able to achieve this extraordinary velocity, because to reach the speed of light, your movement through the flow of time would have to become absolute zero. Have you ever wondered what anchors you to the flow of time? It's your mass, an inseparable form of temporal inertia. So what's the real reason behind this cosmic speed limit? It's not to prevent us from reaching the stars, but to protect a supreme principle, causality. Can you imagine a universe with no speed limit, where signals could travel instantaneously at infinite velocity? In such a world, according to relativity, there would always be a perspective, a moving observer, for whom the effect precedes the cause. You would witness a bottle shattering before you even let go of it. You would see a target explode even before the shooter pulled the trigger. The universe would descend into meaningless chaos where past, present, and future are inverted with no logical order whatsoever. How could history be recorded? Because the speed of light is the refresh rate of this entire reality. This is the maximum speed at which one point in the universe can affect another. It's also the speed at which the fabric of space-time transmits information about any event that has just occurred. If the sun suddenly vanished, our Earth would continue to orbit for another 8 minutes. Why? Simply because the information about its disappearance hasn't had time to reach us yet. Even gravity travels at this speed. Space-time at Earth's location hasn't yet realized that the sun is no longer there. To some extent, we are isolated. But this very isolation, this very limit is what protects us. Every star, every galaxy, even every atom is confined within its own light cone. Sounds rather sad, doesn't it? This implies that, in a way, we are always alone, always one step behind reality, only able to see the ghosts of the past. Yet this very limit is what creates the structure for the entire universe. It allows all events to unfold in a specific order. It ensures that consequences always follow actions. And furthermore, it created life as we know it. Thanks to it, thought and evolution can exist. The speed of light is not a barrier. It is the glue that binds everything together. It is the fundamental immutable rule of the universe. It prevents everything from happening all at once, creating the flow of time. So, the next time you gaze up at the twinkling stars, don't feel disappointed by the vast distances. Don't be saddened by the years of delay that light brings. Remember, the delay of light is the price we pay in exchange for a coherent, ordered universe. The speed of light is not merely a velocity, it is the guarantee of our existence. Have you ever thought that your past, even though it's gone, always remains what it is? But what about the future? It's still entirely within your control, and this very fact will change everything radically.